In this last example for induction that will work out, we're going to actually seek out a formula for a sum of numbers. We had our Gauss summation formula already, which gave us a formula for the sum of the first n positive numbers. And in this example, we're going to come up with a formula for the sum of the first n even numbers. Now, we're going to do it sort of the discovery way first, because it'll be similar to some of the problems on your classwork and homework. But then we're going to realize we actually already knew the answer ahead of time. So let's first try to figure out some patterns, maybe not patterns, but some information about growth rates. So if we were to make a table that had n's, n squareds, and n cubes, we could write out the first, let's do, I don't know, the first 5 natural numbers. And if we write out the squares, we should get 1, 4, 9, 16, 25. And if we write out the cubes, we should get 1, 8, 27, 64, 125. Okay, so great. Now let's look at the sum of the first n evens. So when we look at the sum of the first 1 even, so this is just 1, we get 2, so 2 is 2. The first 2 evens is 2 plus 4 is 6. The first 3 evens is 2 plus 4 plus 6 is 12. The first 4 evens is 2 plus 4 plus 6 plus 8. I just have to add 8 to that. It's 20. And let's go all the way to 5. So 2 plus 4 plus 6 plus 8 plus 10 is 30. Now, we want to think about this as kind of a sequence, 2, then 6, then 12, then 20, then 30. And we want to somehow try to compare growth rates. So here, the jump is 3. Here, the jump is 5. Here, the jump is 7. Here, the jump is 9. So it seems to be going up by not too much. It goes up, the amount it goes up each time is by 2. Here, the jump is 7, and then it's 19, and then it's 37, and then it's, what, 36 plus 25 is 61. So these are much bigger jumps than the squared examples. And now let's analyze the jumps for our sequence. We have 4, we have 8. Of course, it's going to be just whatever even number we added, but I want to include it just to, oops, that's a 6. Just to be clear, that's an 8, and then that's a 10. So our jumps seem to be going up by 2 each time. That mimics what's happening with the squared example. It seems to be going up by 2 each time. So what this is telling me, and once you do enough of these, it'll also be telling you, the intuition is there should be a formula that says that the sum of the first n evens, so the nth even number is 2n. For example, when n is 1, 2n is 2. When n is 2, 2n is 4, and so on, should be somehow a quadratic function. It's probably not n squared on the nose because, well, it's clearly not n squared on the nose, right? It doesn't match. These aren't the squares. We have the squares in this middle column here. It's not the same. But it should be a quadratic. It definitely doesn't grow as fast as a cubic. So this is a guess. The guess is that the growth rate should resemble a quadratic function. And so the question is, well, if it's a quadratic function, what in the world are a, b, and c? So what are they? We need to find guesses for these. And the way in which we're going to find guesses is we're going to go about it in an intelligent way, and then we're going to plug in various n values, and then we're going to get a system of equations. And then I'll tell you what the solution to that system is, but you're welcome to solve it using whatever method you like. So if we take our proposed formula, let me highlight it even. Here's our proposed formula. And this should be true for n bigger than or equal to 1. For n equals 1, our formula says 2 is a times 1 squared plus b times 1 plus c. Or in other words, 2 is a plus b plus c. So here's one of our expressions. When n is equal to 2, we're going to get 2 plus 4 is equal to a times 2 squared plus b times 2 plus c. Or in other words, 6 is 4a plus 2b plus c. And then scroll down a bit more. When n is equal to 3, our formula would tell us 2 plus 4 plus 6 is a times 3 squared plus b times 3 plus c. And so that's 12 is 9a plus 3b plus c. So we have these three linear equations that would, if we could solve, would tell us our coefficients. And we could go further, but actually we have three unknowns, so this is actually enough. And we can then set up the corresponding system. So what's our system? Our system is a plus b plus c is 2. 4a plus 2b plus c is 6. 9a plus 3b plus c is 12. And then we could go about solving our system. So let's do that. I think that the easiest way is by elimination. So let's carry that out. And I even think that actually, so I'll say that I'm not going to solve this system by elimination. I'm going to guess. And I'm going to guess because I kind of already know what the answer is. Let's notice that if a and b were 1 and c were 0, we would get 1 plus 1 plus 0 is 2, 4 plus 2 plus 0 is 6, 9 plus 3 plus 0 is 12. So the solution, there's actually going to be only one, and that's ABC is 1, 1, 0. Now, if you wanted to do elimination, I can help get you started with that. If that's not an acceptable answer for you, which is okay. What you would do is first, since there's all these C's, I would try to start off by eliminating the C's. So I'll do one of the steps of elimination, and then I'll ask you to finish it. Let's make equation 2 minus equation 1. So we're going to subtract equation 1 from equation 2. Or sorry, equation 2 from, equation 1 from equation 2. So 4a, we're going to subtract upwards. So 4a minus a is 3a, 2b minus b is b, c minus c is 0, 6 minus 2 is 4. And we'll also do equation 3 is equation 3 minus equation 1. So if we subtract upwards, 9a minus a is 8a, 3b minus b is 2b, c minus c is 0, 12 minus 2 is 10. And then you can go in and solve for, you can do elimination on the last two and then find A and B and then find C. So I'll stop there, but I encourage you to continue. So this tells us then that A is 1, B is 1, and C is 0, because that certainly is a solution. And so the guess then, let's since we made an educated guess, our conjecture is that 2 plus 4 plus all the way up to 2n. A was the coefficient of the quadratic term, B was the coefficient of the linear term, and C was the constant. So that's just n squared plus n. So now that we have our conjecture, we want to try to prove our conjecture. So how do we prove our conjecture? Well, we proceed by induction. And this is true for n bigger than or equal to 1, of course. And so this is our P of n statement. Our P of n statement is the left-hand side is equal to the right-hand side. For the base case, we have 2 is equal to 1 squared plus 1. That's certainly true. Put a gold check on it. For the inductive step, we're going to suppose P of n is true, which is to say 2 plus 4 plus 2n is n squared plus n. And we show that P of n plus 1 is true, which means we go up past 2n to 2n plus 2, the next even number after 2n, and that should be n plus 1 squared plus n plus 1. And since this is our desired outcome, again, here is our hypothesis, and that's what we're supposing is true. Here's our conclusion. Since we're trying to reach this second equation, let's just multiply it out to see what we're looking for. So the n plus 1 squared is n squared plus 2n plus 1. So that's n squared plus 3n plus 2. That's what we're looking for. All right. So now it's going to proceed just like the Gaussian summation formula step. So we know that 2 plus 4 plus 2n, we give some space. Well, let's not skip steps. Is that, so we're going to add 2n plus 2 to both sides. And if we add 2n plus 2 to both sides, that's going to create exactly what we want. It's going to create the left-hand side of our conclusion. So I'm going to scroll down quite a bit now. When we add in 2n plus 2 to both sides, we're going to get 2 plus 4 plus 2n plus 2n plus 2 is equal to n squared plus n plus 2n plus 2. Just putting parentheses to indicating the term we added. And then the left-hand side matches, so that's good. So let's just put over here, left-hand side matches. So we can stop working there. And on the right-hand side, when we compute this sum, we get n squared plus 3n plus 2. So now the right-hand side matches as well. And so we took P of n, we created P of n plus 1. So thus P of n plus 1 is true. And the proof by induction is complete. So this was a slightly more involved example because we had to arrive at the formula. And we arrived at the formula by kind of comparing growth rates. And that's a strategy that that there's some rigor behind. That we're not going to go into, but you can sort of make a guess like we did and then try to verify your guess. And there'll be some homework problems on that. Now I'm going to be a little bit longer. I'm going to tell you we already knew the answer. So how do we already know the answer? Well, let's do some algebra. So let's take our 2 plus 4 plus blah, blah, blah plus 2n. And what we're going to do is, we notice that every term is divisible by 2. So we can factor out a 2. But so when we factor out a 2 from everything, we get the sum of the first n natural numbers in the parentheses. So we know by the Gauss summation formula that we can replace that with n times n plus 1 over 2. And now what? Well, our 2's are going to cancel. And we get n times n plus 1, which is n squared plus n, which is exactly what our guess was. So we actually already knew the answer, but I wanted to take you through the process of formulating a guess based off of how our sequence of sums grows.